looking at examples of wave. The first example of wave motion, we talked about an ocean wave. Ocean wave. This is the wave on the surface of the ocean, the sea. Then we can also talk about water wave. Water wave. Here, I'm sure some of you may be confused that what is the difference between ocean wave and water wave? The difference is that when you fill a basin or a bowl with water, okay, and then you drop a pebble or gravel into it, that circular concentric thing which forms on the surface of the water is a wave, and this is water wave, the ripples. Okay, so that's the difference between ocean wave and then water wave. Then if you have a stick in your hand and then you apply force to it, as a stick, string or thread in your hand, and somebody holds the other end, and then you disturb it, shake it, it creates a wave along the rope. So we can also talk about wave on a rope. Wave on a rope. Or wave on a string. Then we can also talk about other examples such as earthquake wave, which we call as seismic wave. Earthquake. Earthquake wave or seismic wave. Then we have other waves which are classified as electromagnetic waves. And with electromagnetic waves, we can talk about gamma ray, S-ray, ultraviolet, UV light, visible light, infrared, microwave, radio waves. Yes. All these electromagnetic waves are examples of waves. Okay. So when we talk about some examples of waves, we can list all these. Okay. From ocean wave, water wave, wave on a rope, earthquake wave or seismic wave, gamma ray, S-ray, ultraviolet radiation, visible light, infrared, microwave, radio waves, TV signals. And we can also talk about sound wave. These are some examples of wave. Okay. Now, the formation of a wave. Starts with vibration of particles. The formation of a wave actually starts with vibration of particles. The example I illustrated, the ocean wave, how it is formed is that the strong wind which blows on the surface of the sea. So the wind splashes on the surface, and the energy of the moving of the wind is picked by the water molecules. Okay, when the energy is received by the water molecules, it vibrates the water molecules. Now, what happens is that, assuming this is the first water molecule, second, in that order, continuously, what happens is that this one receives the energy, then vibrates either vertically, up and down, and then because of their closeness, okay, this one vibrates and hits this one. This one also vibrates, and the vibration hits this one, on and on and on. Okay, the energy received by the first is transferred to this. So the source of every wave is the vibration of the particles of the medium. Please, is that point understood?
Yes, please.
All right. Now let's Adjoa Ipia, Gerard Inshira, Josephine Oye, Windows. Who is Windows using Windows? Who is that? Oh, no, no, okay. All right. So let's look at, we've listed examples of waves. Okay, and we have also seen how a wave is initiated. The wave motion is initiated. It is by vibration of the particles of the medium. This vibration is transferred. So the first one vibrates, the vibration hits the other, on and on and on. And the energy, as this thing continues to happen, the energy received by the first, second is transferred on and on and on. And that is what creates the wave as we see. Okay. Now let's look at how waves are classified. Classification of waves. So we've talked about types. Under classification, we are going to group these examples of waves based on certain facts. Okay, so when we talk about classification of waves, the waves, examples of waves as listed, they have common features. So we look at what and what you have and then put you under common umbrella or room. And that is what we mean by classification of waves. Waves can be classified into, we have three different ways of classifying waves. But at your level, we'll look at only two of the three. We have what we call as mechanical waves and electromagnetic wave. And the third classification is matter wave. So we have one, mechanical waves, then two, we have electromagnetic then we have the third classification is matter wave. What do we mean by mechanical waves? So The subtopic is classification. Classification of waves. Classification is similar to taxonomy, grouping in biology. Okay. In taxonomy, we are grouping organisms based on certain common features they have. So over here under classification, we are grouping this based on certain facts or common features they have. One, when we talk about mechanical waves, we are looking at all the waves that can be propagated or transported from one point to another on condition that there is a medium. So we say that mechanical waves are waves that require a medium for propagation, meaning that this class or grouping of waves are such that when you don't give them a medium or a conduit, they cannot be propagated. A typical example of one of the mechanical waves is sound wave. You know, before you can speak for a colleague to hear you out, there must be air molecules. If there is no air, when you speak, nobody hears you out. Okay, so they say in space, I've not been there. That's why I said they say in space, when you speak, nobody hears you because there is no air. So in sound wave will require air molecules before it can be transported from one region to another. Another example of a wave which can be put under mechanical is ocean and water wave. If there is no ocean or if there is no water, the ocean wave, which we see when we visit the seashore, can never be formed. So ocean wave and water wave will require the water medium to be transported. Okay, so when we talk about mechanical waves, these are all grouping of waves that require a medium for their propagation. So mechanical waves require a medium for propagation. A medium for propagation. So example of waves that can be classified as mechanical. We have one, ocean wave, water wave. We have wave on a rope, wave on a rope, seismic or earthquake wave. If there's no soil or rocks, earthquake wave can never happen. Okay. Can you talk about any other wave? Okay, we haven't listed sound wave. Can you talk about any other wave which can be classified as mechanical apart from what I've listed? Yes, Gerard, I thought you were coming in.
Oh, no, sir, no, sir. So I'm thinking.
Never. I'm coming in. Nanama, are you there?
Yes, please.
Oh, okay. I just read the message that was sent to me. Okay, so let's also talk about another. So, Nanama, apart from this, apart from ocean water on a wave on a rope, seismic wave, and can you talk about any other wave which can be put under mechanical wave? I think we can also put here tidal wave. Nanama, do you have any other example in mind?
No, please.
Okay, then let's look at electromagnetic waves. Electromagnetic waves are shortened as EM wave. EM. Instead of writing electromagnetic, we shorten them as EM wave. For electromagnetic waves, they are such that they do not require any medium. The point is that if there is a medium, they can be propagated through the medium. If there is no medium, they can also be propagated. So it's a dual kind of thing. Please, I'm coming in. Yes. That is a dual kind of thing. Whether there's a medium or there's no medium, they can still be propagated. And example of electromagnetic waves, EM waves, are all the waves listed from gamma ray, X-ray, UV, visible light, infrared, microwave, up to TV signals. Okay, all the electromagnetic waves have something in common, and what they have in common is that they all travel at a speed of 300 million meter within a second. Okay, so the EM waves all have this feature that they travel at a speed of 3 times 10 to the power 8 meter per second. So all the waves under the electromagnetic wave spectrum, from gamma, X-ray, blah, 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 up to TV signal, are all electromagnetic waves. And they wouldn't require any medium. That is why, you see, before you could call somebody, okay, abroad or in overseas, you could dial, and sometimes your call, okay, your call can go to space satellites, the satellite in space. Even before that was the only means. You call and it is picked by international station in Ghana here, and it is given to satellite in space. The satellite in space also has their main transmission office in US. So the funny thing is that when you call somebody in Togo, even in Togo, the call will go to space satellite. The space satellite would give your call to the main office in US. Then US will look for the destination of your call. Now, where is it going? Then they will route your call back to Togo. Okay, and this is the reason why whenever you call in any African country, the billing is higher than when you call somebody in US. So when you call somebody just in Togo here, the cost or the charges is greater than calling somebody in US. It's because of this reason. Okay, before then, all calls moving outside Ghana has to go to US, go to satellite, and then go to US. But this time, cables are laid through the sea to US, America, and Europe direct. So depending on how the telecommunication wants, they can route their cable through the sea or through or give it to satellite to send it. So in space, there is no air. Yet electromagnetic waves could reach there and go. So EM waves does not require any medium for them to be propagated. Okay, that's the difference between mechanical waves and electromagnetic waves. Please, any question? Do you have any question?
No, sir.
Okay. Israel, are you there?
Sir,
Yes, please.
Ask your question. If you have any. All right.
sir, please, I have a question. So,
Okay, ask.
please, can you explain it again why it's cheaper to call somebody outside, but then in an African country, it's
Yes. So when you call somebody in US, you pay less. And US is, I mean, quite a greater distance or far distance from Ghana. Meanwhile, when you call somebody in US, it's less expensive compared to calling somebody in Togo, which is just here, and then Cote d'Ivoire. The reason is that, you see, before Africa, we don't have our own communication satellite. So we hook on to the international communication satellite. So when you are in Ghana here and you call somebody, your call has to be given to international satellite in space. So this is Ghana, but your call will be given to satellite in space. This satellite in space has their main office in US. So from space, your call will go to US. Okay. Then from US will look for the destination of your call. So imagine you are calling somebody in Togo, meaning your call must come back to Ghana, close to Ghana, because Togo can be just here. Or let me even route it this way. Togo is here. But look at the destination. Space, from space to US, US to a country which is close to Ghana. Meanwhile, if you are calling somebody in US, it's just from space to US. So please, this is similar to wanting to go to maybe Tamale, but from Accra or from Cape Coast, you don't have, or you can't get a direct car to Tamale. So you must go to maybe Takwa before you pick a car from Takwa to Tamale. So the transit would be factored, and it will make the whole calling process expensive. Nanama, are you okay?
yes, please.
So this is the reason why. If we had our own communication satellite, then calls from Ghana to space, then space, our satellite will give it to Togo direct. But we don't have our own satellite. But it is these days, it is a bit better because cables are laid through from Ghana through to neighboring countries, Europe and all that. So that's the reason why calls these days are not so much expensive, because of fiber cable. Cables are laid from country to country direct by the telecommunication companies. All right. So let's look at another classification. So we've talked about the third one, the third classification, which matter wave, is not talked about at your level, because this is a wave which is exhibited by the electrons, okay, and protons. So it is within matter. That is why we don't discuss it at your level, okay? So at your level, we only talk about mechanical waves and then the electromagnetic waves, and leave matter wave to maybe when you go into physics properly. Quantum physics. Another classification which we'll talk about is transverse wave and longitudinal wave. Please, the classifications are not types of waves. The types or the examples are what I gave you: sound wave, ocean wave, water wave, and those other examples. For mechanical, we are only classifying the examples based on certain common features they all have, right? So don't see that as an example. All right, then, so what is transverse wave? Gerard, are you there?
So I'm there.
What is transverse wave? Can you tell us about what transverse wave is? Oh, Nanama, can you share your experience with us? Nanama, are you there? Gerard, are you there? Hey, everybody is quiet too. Okay. All right. You see,
Samuel.
I earlier said that the source of every wave is the vibration of the particles of the medium. So when the particles vibrate, it begins the wave. The vibration affects other particles on and on and on, and it creates that wave. Okay. So when we talk about transverse wave, this time we are looking at how the particles vibrate, and as the particles vibrate, how is the wave formed? So this particular classification, talks about how particles vibrate, particles of the medium vibrates, and how the wave is created or formed. So the vibration of the particles creates the wave. But the question is that, how are the particles vibrating? And when the particles vibrate, how is the wave produced? So let's use this as the particles of a medium. under one classification, which we'll talk about, the particles actually vibrate in this manner. The vibration of the particles vibrate in that up and down manner. Up. Down.
This one. The question them talks as you can remove this chili.
Gerard,
Sir. Yes, sir.
you are disturbing.
Sorry.
So these particles here vibrate in an up and down manner. So it's like people, okay, standing in this manner, one after the other. Then they move up and down. Now, as the particles vibrate in that up and down manner, okay, the energy transmission, which is actually the wave, the transfer of the energy, meaning there's a source which must cause the particles to vibrate. Okay, so when the source hits the first particle vibrates up and down. It hits this one and it also vibrates up and down. Now, as the particles vibrate in this manner, the energy is transmitted perpendicularly to the direction of vibration of the particles. Okay, so under this classification, we have particles vibrating in an up and down manner, and the energy transmitted through the particles is perpendicular to the vibration of the particles. So this arrow is a transfer of the energy, which is actually the wave. Okay, this kind of wave formation is what we term as transverse wave. So a transverse wave is that kind of wave whereby particle vibration is perpendicular to the propagation of the wave. Okay, so in a transverse wave, the vibration of the particles is perpendicular to the propagation of the wave itself. Please note the definition. So in a transverse wave, the vibration of the particles of the medium is perpendicular to the propagation of the wave. That is transverse wave. And examples of waves that can be classified as transverse, we have all electromagnetic waves. Electromagnetic waves are transverse waves. Then, apart from all electromagnetic waves, we can also, other examples of transverse wave can be wave on a rope, earthquake or seismic wave, okay. Ocean waves are mixed, okay, are mixed. It can the wave formed at the surface are transverse. The wave formed at the deeper part of the ocean is electromagnetic. So as for ocean wave, it's mixed. But when we talk about transverse waves, all electromagnetic waves are transverse wave, wave on a rope, seismic wave are examples of transverse wave. Now, the other one, which is longitudinal wave. As for longitudinal waves, a typical example is this. You see, whenever you open a syringe, okay, pull the plunger out, and then you exert pressure just to close the volume, or you close the plunger, or you exert force on the plunger, the syringe. You create a longitudinal waves with the air trapped within the syringe. So what happens is that in this particular kind of wave, we have the particles of the medium vibrating back and forth. They vibrate back and forth, okay, in this manner. So this one vibrates back and forth, and as a result, the energy transmission, which is actually the wave, is propagated in that same direction. So as the particles vibrate back and forth in this manner, the energy is also, or the wave propagation is also parallel to the vibration of the particles of the medium. So for longitudinal waves, we say that the particle vibration is parallel to the propagation of the wave. Don't forget, the transmission of the energy is actually the wave. So as the particles vibrate in this manner, the wave is also propagated parallel to how the particles are being vibrated. So when you push the plunger of the syringe, okay, the particles move in this manner. Air particles within the syringe move back and forth, and the energy propagated goes parallel to it. And this is how we describe a longitudinal wave. So in a longitudinal wave, the vibration of the particles of the medium is parallel to the propagation of the wave. An example of longitudinal wave, we have sound wave. Sound wave is a classical example of longitudinal wave. So in a longitudinal wave, the vibration of the particles is parallel to the propagation of the wave. So example, we have sound wave, and then wave at a deeper or deep section of the ocean. So as for transverse wave, we have a lot of examples. All electromagnetic waves are transverse wave, wave on a rope, earthquake or seismic wave. Okay, and there are other examples. Examples of a transverse wave. But for longitudinal wave, we can only talk about sound wave, and then whenever air column, which is trapped in a syringe, is pushed out. Okay, that is also an example of pushing air column out of a syringe. Also creates longitudinal wave. So these are the wave classification. So we've seen what a wave is: a traveling disturbance that carry energy from one region or area of a medium to another. And a wave transfer energy but not matter. Hence the saying that the sea never gets flooded, because what is actually pushed isn't water, but it is energy of the wind, blowing wind. Then we've seen classification of waves, mechanical waves, and then electromagnetic waves. And then examples of waves we can classify under electromagnetic and then mechanical. Then we've also seen another classification which is based on how particles of the medium vibrate and how the energy which actually causes the vibration of the particle is propagated. So in transverse, the particles vibrate, a particle vibration is perpendicular to the propagation of the wave. And we've seen example. Then in longitudinal waves, the particle vibration is parallel to the propagation of the wave itself. And we've also talked about example. Okay. Let's then move on to the wave profile. Wave exercise. The wave profile. The wave profile. How do we visualize or simulate a wave? It has the name, or we use the name wave, because you see, wave is related to this. And this is a repeated something. So a wave is actually a harmonic something. When something is harmonic, that thing is repeated. The reason for which we use the word wave, because wave, I'm waving at you, and this is a repeated thing. So a wave is a harmonic something. Okay, a wave is a harmonic something. So if we want to represent or use something to represent a wave, we represent a wave using a simple harmonic function. So a wave is represented as a sine function. A wave is represented as a sine. Let me also use cosine function, because both sine and cosine functions are harmonic. What is a sine function? In your mathematics, a sine function is represented as this. So this is how we symbolize a wave using a sine function. equal amplitude. So a wave itself is a harmonic function. This is what we call as a sine function. So technically, we say that a wave is a sinusoidal wave function. It's represented as a sine, so it's sinusoidal. Now, this is also in SHM. This is the displacement function or graph of a body executing simple harmonic motion. So this is displacement y against time or x. It can be y against t. Okay. Now in simple harmonic motion, the maximum displacement, which is measured from the equilibrium position to a point where we have maximum vibration of particles upward, and then a maximum vibration of particle upwardly is known as crest. Then the maximum vibration of particles, but downwardly of particle, we have what we call trough. So it means a wave has crest and trough. A crest is represented as C, trough represented as T. Now, when you measurement from the equilibrium position to where we have maximum vibration of particle, we measure what we call the amplitude. So the amplitude of the wave is from the equilibrium position to where we have maximum vibration of the particle. So it can be A up here or A down here. Please, because you have done SHM, I'm just going through this quickly. Okay, so a wave, this is what we are calling as the wave profile, how wave actually looks like. And this is actually what we call as progressive wave. Progressive waves are traveling waves that can be propagated continuously throughout the medium. We'll actually go through a progressive wave, but this is how we represent a wave, whether electromagnetic waves or transverse mechanical waves, transverse or longitudinal. If you are drawing something to represent a wave, this is it. What is this horizontal line? When you have a medium, this is water, and the surface is calm. There's no wind blowing the surface. You realize that the molecules are at rest. So the horizontal line, let's represent that by X. The equilibrium position represents when there is no disturbance to the medium at the equilibrium position. Now, when an external source, such as wind, blows on the surface, then the molecules begin to move up and down. And that is what forms or creates the wave profile. Okay, so the X represents the equilibrium position of the wave. Now, the amplitude represents the maximum displacement of the particles of the medium. So the energy has actually moved the water molecules, and the maximum possible displacement is what we are representing by the amplitude. So this is the wave profile. Please, any question? Ebiadom, are you there? Oye,
Yes, sir.
Oye and Josephine. Nanam, are you there?
Yes, please.
Okay. Then let's look at the measurable properties of a wave. The measurable properties of a wave. Measurable properties of a wave. Parameters of the wave or parts of the wave we can measure. We can actually measure the amplitude of the wave. Okay, so the amplitude of the wave is measured from the equilibrium position when the surface medium is not disturbed to when it is disturbed, and we have maximum displacement of the particle. So this is A. So the amplitude is measured from the equilibrium position to crest, or from the equilibrium position to the trough. This is how to measure amplitude. So when you are given a wave profile and you are asked to measure the amplitude, you measure it from the equilibrium position to the maximum particle displacement, either up or down. And either up or down, the value is the same. So let's define it. The amplitude. We've done SHM. Akuya, how would you define amplitude? The word amplitude, whether from SHM or circular motion. How would you define amplitude? Akuya Adoma.
There's a maximum displacement of an oscillating body.
Okay. So here, the maximum displacement of a particle. Okay, an oscillating particle. All right. In terms of wave, we define the amplitude as the maximum displacement, okay, of the wave. It's that amplitude is a measurement of length. So its SI unit is the meter. Now, the amplitude of a wave indicates the energy carried by a wave. So if you want to determine the energy carried by a wave, then determine its amplitude. So amplitude of a wave determines the energy carried by a wave. Gerard, is Kenneth there?
Please, I'm here.
Okay. So the amplitude determines the energy carried by a wave. Let's be practical. You see, when you visit the seashore and you see the ocean wave coming, the height from the water surface to the wave itself will determine whether you are to run away, okay, run away or meet the wave. Some waves are such that, you see, from the water surface, their height is very high. What you see on the surface of the water is actually the amplitude. So when you realize that the height of the wave is from the water surface is so high, then you will decide to run away. Why are you running away? Because you think that thing comes with a lot of strength, energy. So if you don't run away, it can displace you and get you drowned. So if you want to measure the energy carried by a wave, it is the amplitude. The amplitude of the wave determines the energy it carries. Adwa, are you okay? Oye. Oye,
Yes.
yeah. Another measurable property of a wave is that we can also talk about a wave's frequency. Frequency. We can also measure the frequency. Inshira, are you there? Hello, Inshira.
Yes.
I want you to revisit SHM and tell me what frequency is. Inshira, what is frequency of an oscillating body? You have an idea? If you have not forgotten.
The number of oscillations per second.
Okay, thank you. So here is the number of complete oscillations. Complete. The complete is very, very important. Okay, the number of complete oscillations in second. Within a second is a frequency. And a wave, yes. It is also defined as the number of complete cycles of a wave within a second. So frequency in wave motion is the number of complete cycles or complete wave within a second. Let's try to understand what we mean by a complete wave or cycle. When a wave is complete, one way of determining a complete wave is that you see, when a wave has just this upward pulse, this pulses, this pulse. So this is an upward pulse, this is a downward pulse. Okay, a complete wave has one upward pulse and then one downward pulse. So this length constitutes a complete wave. So if I'm to count the number of complete waves I have here, I have 1, 2, 2.5. This is another complete wave. So I have 2.5. So this is one way of identifying a complete wave. Another way of identifying a complete wave is that in fact, the length of a complete wave is actually termed as wavelength. The length of a wave is known as wavelength. represented by the symbol lambda, the Greek letter lambda. Okay. Another complete wave can be determined by the distance between successive crests and troughs. So a wavelength is defined as the distance between successive crests or troughs. Crests or troughs. So this is the definition of a wavelength. So if I determine the distance between a successive crest, this and this are successive crests, then the distance between them gives us a full wave or lambda, or successive troughs. This is a trough, a point of maximum particle vibration, but below. These two are successive troughs. So the distance between them, this also constitutes wavelength. So identifying a complete wave can be one upward pulse, one downward pulse, or successive, the distance between successive crests or successive troughs. Okay, that is how to identify a complete wave or a complete cycle. Please, is that okay?
Yes, sir.
All right. Those of you who are not talking, you'll fall asleep, so begin to contribute. So we've seen what we mean by frequency. Frequency is the number of complete cycles or complete wave within a second. What's the SI unit? Nanama, what's the SI unit of frequency?
Is T raised to the power negative 1.
SI unit.
Sorry. Second.
Come again.
Second.
Per second is the derived unit, but the SI. Hertz.
Sorry.
Okay, hertz. Josephine, what is the SI unit of wavelength? Josephine, what's the SI unit of wavelength?
Study of this lambda.
SI unit. Lambda is the symbol. The symbol used to represent wavelength is lambda. But what's the SI unit?
Meter.
Pardon?
Meter.
Meter. Because it's also length. Is that okay? All right. Then so we've talked about the measurable properties. We've talked about the amplitude, frequency, wavelength. Then let's look at the period. Period. Capital T. What is period in SHM? Let me call somebody to help us. Adwa, under SHM, what do we mean by a period? What is a period?
The total amount of time.
The what? Total
Time.
Adwa won't buy it. I won't buy it. Nanama, sell it to me. Maybe I can buy it. What is period? Whether in SHM or a wave.
Time taking for
Hey, Nanama, your voice is so thin.
Please, the time or the time intake.
No, it's a time, but you are not hitting the nail properly.
Mistake.
Adwa.
The time taken for a complete oscillation.
Exactly. So it is the time taken for a complete oscillation. Okay. It is the time taken for a complete oscillation. Now, under waves, are you there?
Yes, please.
And now order.
Please, I'm here.
Okay, so this is a complete cycle or a complete wave. When the wave is being created, the time taken to make a complete cycle, okay, is what we are terming as a period. So maybe this is 2 seconds. If it is displacement against time, okay, if this is 2 seconds, then the next complete wave, this will also be another 2 seconds. So this will be 4 seconds. 2 plus 2. This is half of the complete cycle. So this will be 5. Then if we join 6. So the time taken to make a complete, to have a complete cycle of wave is what we are terming as the period. Okay. Okay, then maybe I didn't get you right, Nanama. All right, thank you. So, what is the unit of period? The period is represented as capital T, and it's a time. Period is a time for a complete wave. So, its SI unit is also the second. All right. Now, the next measurable property of a wave, which we have to understand, is the velocity, the wave velocity, okay, or speed, the wave speed. Please do not forget that wave frequency and period are related. Frequency and period are related by the same equation. T is equal to, period is equal to the total time divided by the number of complete waves or cycles. Okay, the total time divided by the number of complete cycles, and frequency is also equal to the number of complete cycles, okay, divided by time. But for frequency, the time is actually 1 second. So it is F is equal to N over T. But usually we peg it at 1 second to determine the number of complete cycles. And so looking at this, still F is related to T by this equation. So this is an equation we saw in simple harmonic motion. We also saw in circular motion. It is also showing up in wave motion as well. It is not different. All right. Now, speed of a wave. Speed. You know, speed V is equal to distance over time taken. And the waves, we look at the wavelength for a complete cycle or complete wave. The length of a complete wave is what we are terming as the wavelength, lambda. So for a complete wave, the distance is lambda. The time taken to make or to execute a complete cycle is the period, capital T. And so V is equal to lambda over T. Please don't forget that here, when we look at one complete cycle. And so in that case, because F is equal to 1 over T, and what we have here is also equal to lambda times 1 over T, then we can say that this is F. So we have the speed of a wave being equal to F times wavelength, lambda. And that is why we, for waves and SHM, the velocity or the speed of a wave is given by F lambda. Okay, so this relation is obtained upon considering just a full cycle of a wave. Okay, speed has the unit as meter per second. Please, are we okay?
Yes.
All right. All right. Now, I think let's solve one or two questions before we move on. I think where we've got into, we can apply this in question solving. So question 1. Are you ready? Please, I'm dictating, so get ready to put it down. The speed of a radio wave is 3.0 is 3.0 times 10 to the power 8 meter per second. The speed of a radio wave is 3.0 times 10 to the power 8 meter per second. If a radio station broadcasts on a wavelength of 1,500 meter, 1,500 meter, what is the frequency of transmission? What is the frequency of transmission? The speed of a radio wave is 3.0 times 10 to the power 8 meter per second. If a radio station broadcasts on a wavelength of 1,500 meter, what is the frequency of transmission? This one should be 2 minutes. Just 2 minutes. Are you true? Hello, are we true? Ajua, Nanama, Israel, what did you get? Hello, Israel. Ajua, what did you get? Otubia,
These 2 times 10 is about 5 times
meaning 200, 200,000.
1,000.
I think that's correct. Gerard, I saw your answer. Okay. I think that's simple. It's you are giving the speed and you're also giving the wavelength. So you have to use V is equal to F lambda. Okay. V is equal to F lambda. Make F the subject and you are there. Question 2. Question 2, are you ready?
Yes, sir.
It takes 4 crests of waves. It takes 4 crests of waves to cross a given point in 1 second. It takes 4 crests of waves to cross a given point in 1 second. If the distance between any 2 successive crests is 20 centimeter, if the distance between any 2 successive crests is 20 centimeter, calculate I. If the distance between any 2 successive crests is 20 centimeter, calculate I, the frequency, I, the period, I, wavelength, IV, the velocity of the wave. It takes 4 crests of waves to cross a given point in 1 second. If the distance between any 2 successive crests is 20 centimeter, calculate I, the frequency, I, the period, I, the wavelength, and IV, the velocity of the wave. Start with this. This will take 5 minutes. This will take 5 minutes. let me give you a clue. So it takes 4 crests. It takes 4 crests. So indirectly, this is what they are saying. You know, crests do not move all alone. The crests move with troughs. Whenever there's crest, there must be trough. So it takes 4 troughs. Crests. This is 1 crest. I think it's not showing properly. So let me bring it down a bit for you to see. So this is ideally 1 crest. So it takes 4. This is another crest. This is another crest. Then the last. But the point is that crests do not move. Whenever there is crest, there must be trough. So it's actually like this. Trough, crest, trough. It should have the same amplitude. So this is actually the wave profile. Okay. It takes 4 waves to cross. It takes 4 crests of waves to cross a given point in 1 second. So it means the time taken for the formation of this 4 crests. This is 1. This time must go with 1 second. That's what it means. Please, are we okay? And we are told that the distance, if the distance between any 2 successive crests is 20 centimeters, if the distance between any 2 successive crests, it can be this. This is 20 centimeters. Any 2 successive crests is 20 centimeters. Then calculate I, the frequency, the period, and so on and so forth. So this is what will guide you. Who is through with the first question on the frequency? What did you get for the frequency?
Please, 3.5.
Come again.
Please, 3.5.
3.5. Okay, that's Gerard's view. Who else is true with the frequency? Josephine. Josephine.
Mr. Adrian, please I have a question with the diagram on the board.
Ask.
Please, since you said every crest has a trough, that means that the last crest will not get a trough.
We can give it a trough. Okay. I was just using this to represent the 4 successive. So it's actually like this. So this should be 1 second. So it takes 4 successive crests, meaning that we have 4 complete cycles or weeks.
Sir,
Hello.
sir,
Yeah.
is why we adding a trough to it when the question did not ask.
No.
Sir, there's
Waves do not move with. I gave you the wave profile. So every wave has a crest and a trough. Okay. The question is
Yes, sir.
crafted in that manner for you to actually apply that. If we draw just crests, it doesn't qualify for a wave. Are you okay?
Sir,
But then the 1 second, you see, you are talking about 1 second. So it could be that the 1 second ended at the crest.
No, the 1 second must end here. Meaning, all that the question actually means is that we have 4 complete waves, and it takes 1 second for the wave to move to that point. So it has to end, the 1 second must be here. Crests do not, move all alone. It doesn't, the wave profile is at crest and a trough. So Gerard, look at your answer to the question 1 again.
So I want to change it.
And that's why I said I'm asking you to do so. So what did you get for frequency?
So I have frequency to be 4.
It's 4 hertz.
Mm-hmm.
Yeah, the answer is 4. Then, please, the rest of you, are you following? So these are the 4
Yes.
this, and this. But each crest goes with a trough. That is why the distance between successive crests, okay, each crest must go with trough. So frequency is equal to number of complete waves within a second. So the complete wave 4 divided by the time 1, giving us 4 hertz, or 4, yes, per second. All right. If once we have the frequency, the period must be easy. Period is equal to 1 over f. So the period must be 1 on 4, which is 0.25 seconds. All right. What it means is that, look at the time. This is a complete cycle. So this is 0.25. This is another complete cycle, 0.25, giving us what? 0.5, right? This is another complete wave, 0.75. Then 1. Then the wavelength. Yes. I want one of you to tell me what the wavelength. Gerard, keep quiet. I want somebody else, one of the ladies, to tell us what the wavelength is. Adwa.
0.2 meters.
0.2 or the 20 centimeter. Are you okay? As for the wavelength, the question told us that the distance between a crest and its adjacent, I'm reading a different question. We are told that if the distance between any 2 successive crests is 20 centimeter, and that is the wavelength. So either 0.2 meter or 20 centimeter. Then the velocity. Josephine, calculate the velocity for me.
Yes, I have 0.8 meter per second.
Come again.
Yes, I have 0.8 meter per second.
That's correct. That's correct. So V is equal to F lambda, and frequency 4, wavelength 0.2. 0.2 is 2 on 10. So numerator 8 on 10, which is 0.8 meter per second. Okay. Nanama, are you okay with the question?
Yes, please.
All right. Ishra, are you okay?
Yes, please.
All right. Okay, so it's 5 minutes past 9. I'll send you work sets to do. But please, from the next meeting is on Friday. I'm going to set my stuff today. In fact, the on and off situation of the machine delayed a bit, so I'll fix the problem and then, I mean, we utilize the time to the fullest on Friday. Is that okay? In the meantime, we will close now and I'll send you work sets. Please, is that okay?
Okay, sir.
All right. So good night to all of you. It's a pleasure having you for today. We are going to continue on Friday. Bye-bye to all of you. Okay. All right. Hey, Ekuya Doma. Ekuya went. I'll send you the video so you can review it. Okay. Nishra,
Yes, to state, yeah.
I'll send the video to you as well.
Okay.
Oh, bye-bye.